Good to see you here. And you will speak about hadronic interactions at ultra-high energies. Now the floor is yours. Go ahead, please, Lorenzo.
Okay, thank you very much. And I thank you, the organizer, for having invited me. And I'm very sorry I cannot be there with you. And this is some health issues. But anyway, so this is my talk. I will speak about hadronic interactions at ultra-high energies with extensive air showers. So this first transparency shows the scope of my talk. I don't know if you can see the pointer. I hope you can see the pointer. Can you? Yeah, okay. I assume you can. So nature goes from the microscopic world, from the interactions. It builds extensive air showers, and then we have detectors that detect these showers. The physics point of view, or at least the experimentalist point of view, is that we take the detectors, we make measurements, we build, we reconstruct the extensive air showers, not with all the information, with some subsamples of information, and we want to learn things about the basics of those interactions. And my object of study, my specialization, is extensive air showers. And for a complete review on this topic and on the problems of hadronic physics with extensive air showers, the Muon puzzle, and many other things, you have here this reference, which is a very complete review on that. So, extensive air shower. This is a picture of a cartoon picture of an extensive air shower, where we have the first interaction, and then we have a multiplicative process which reach up to 10 to the 12, 10 to the 13th particles and interactions. I'm thinking about a shower of 10 to the 19th, so well above the ultra high energy regime. So we go basically from as an ensemble of information of the order of 10 to the 12 independent observables, variables, to at most perhaps 10 independent observables. This is what we can learn from the extensive air showers. We can measure things which are macroscopic. We cannot measure things which are microscopic, or we could at the end of the shower, right, with particle detectors. But for the object as a whole, or for the extensive air shower, we can measure of the order of 10 independent variables. So the question, the basic question we wonder is, how much information about the mass of the primary and interactions of the primary is possible to recover? And in particular, obviously, from the first interaction, which is the most interesting one, because it's well above the LHC. This is well above the energies reached by man-made accelerators. This is very interesting. So we go now, let me explain what is the basics of the air shower as a feedback and as a coupling of different showers. So basically we have, when the cosmic rays enter the atmosphere, we have hadronic interactions. Then we have mostly many pions, baryons, and some other mesons. Many of these mesons, mainly the pies, the charged pies, reinteract again. So this is self-sustained cascade, which is the hadronic cascade. Sometimes, or 1/3 of the times, the pi seed or one of the mesons decay and produce, they feed the electromagnetic cascade, which is self-sustained, right? And when the charged pions have low energy, when they don't have enough energy to interact again, they produce muons. So muons will be the tracers of the hadronic cascade, and then the electromagnetic cascade can be seen because they emit radiation through the interaction with the atmosphere. But most of the information we will get of the hadronic cascade is by means of muons. So the hadronic cascade is the main engine of the whole cascade. And we have two cascades which are coupled, the electromagnetic and the hadronic cascade. In the first interaction, I show here a pie chart of the different particles produced in the first interaction. So this is a pie chart of the multiplicity for one of the models, which is one of the state-of-the-art models after being tuned by the latest LHC data. So we see in shades of blue, we see the hadronically interacting particles. So most of the multiplicity comes from pions. Then we have some kaons and some baryons. Okay, and it's practically the same for peer interactions and pair and kaoner interactions. Approximately 1/4 of the multiplicity goes to pi zeros and to charge, photons and electrons. When we jump to the energy fraction, the picture is more or less the same, but we see, so this is the sum of the energy carried by the secondaries. We see that the baryons are a bit more important. It's reduced the fraction of all the other particles, and baryons become more important for the three type of interactions: proton-air, pion-air, and kaon-air. These two, the pion-air and the kaon-air interactions, are typically interactions after the first interaction, which happen in the development of the shower. So it's important to think, typically people think of multiplicities when they think about the growth of the electromagnetic cascade, and when they think of the full cascade, and when they think of how it behaves, but it's more important the energy fraction taken by the particles, because this is what governs the coupling of the electromagnetic and the hadronic cascade. And in this equation here, we can see that the fraction of energy kept into the hadronic cascade after each interaction is basically the multiplication of the fraction of this energy after each generation. So the fraction of energy after n generations is basically the multiplication of the fraction of the single generations, which is, this value is typically around in between 2/3 and 3/4, more or less. And here we can see this is the evolution of this fraction of the particle at the number of generations, and we can see that here in this corner of the picture, it would be the energy kept into the hadronic cascade. This would be the electromagnetic energy, and we see that after 2 or 3 generations, most of the energy is already transferred to the electromagnetic cascade. So the energy is building up to the electromagnetic cascade and is getting out of the hadronic cascade. So after 2 or 3 generations, the hadronic and the electromagnetic cascade are decoupled. And we can conclude from here also that the electromagnetic cascade is sensitive to high energy physics, whereas the hadronic cascade is more sensitive to the observations we do on the hadronic cascade is more sensitive to the high and low energies, because the muons are produced at the very end of the hadronic cascade, whereas most of the information we get from the electromagnetic cascade is driven by the first interaction, because it's the greatest contribution to the energy. And here we can see in the right side, we can see the evolution of the electromagnetic cascade for an ensemble of iron showers. And we can see the evolution of the tracers of the electromagnetic cascade. So this is the positions or the depth where the muons are produced, and the muons are produced after the pion decay. So this is the tracer of the hadronic cascade, and this is directly the electromagnetic cascade. And then we can define the maximum of the electromagnetic cascade, which we know is sensitive to the mass composition, but also we can define the maximum of the hadronic tracers, or the maximum of the muon production depth, which is also sensitive to composition, but it's also sensitive to other stuff, because we will see what problems this has. And well, this is just a cartoon of what I said. So we have to distinguish between the muon production depth distribution. So this is how the muons are produced. So this is the hadronic cascade, but the cumulative of this cascade is basically the total number of muons. So the number of muons is being produced, is being accumulated, and some of them disappear because of decay. So this would be the profile of the total number of muons. In a sense, this number would be equivalent to this number, whereas this one is the differential of this cumulative, obviously. So let's see how the different hadronic parameters impact the development of the shower. So this work was done by Ralph Ulrich and some colleagues already more than 10 years ago, and by a smooth variation of basic parameters, which are the cross-section, the multiplicity, and the elasticity, and the fraction of pi zeros. He could study by a smooth change, which is depicted like that. So it's kept at low energy, so there is no variation, and then a smooth function changes the evolution above this energy threshold. You cannot introduce a sudden change. So you can study what is the impact, for instance, in the number of muons and in X max. So in X max, for instance, the cross-section changes the X max a lot. Of course, we know it. And for the number of muons, for instance, if you change the fraction of pi zeros, then you put more hadronic particles, then you also change the number of muons. Oops, this is not changing. One of the things, one of the direct measurements, and this is related to the previous transparency because it was basically they used the same function to modify the cross section. One of the direct measurements that can be done with air showers is the proton air cross section. So by moving the cross section in a smooth way, you change the tail of the X max, the depth, the deep tail of the X max distribution, and by making an inverse map, we can reconstruct. So we can compare with actual observations, which are here, and we can obtain the actual cross section. So which is here for different cosmic ray experiments, and we see that it agrees more or less well with the expectations from different hadronic models. This was a quick reminder of this measurement. But some other parameters, like the ones I said, the elasticity, the energy fraction going into pions, they have, for instance, here we have the energy fraction kept in the hadronic cascade. We see that there is quite room in between the shadowed region is the difference, the allowed space in between different hadronic models. We see that there is some uncertainty. Also for the cross section, there is little less dependence for the inelasticity. And sorry, this was the cross section, and this is the multiplicity, and this was the cross section. Sorry. So there is some room. The models have some room for. They don't have a straight. They don't coincide in the predictions, and this introduces some uncertainties in the prediction of the main observables of the showers. So the electromagnetic shower is very well understood, and this translates into X max being the observable, which is being used for mass inference. But the muons, they have lots of room variation from model to model. They have large model uncertainties, and this is the reason why typically muons are less trusted to build to reconstruct the mass composition of cosmic rays. In regarding the distributions observed at ground, both the electromagnetic and the muon components show universal characteristics, which I will show here. For instance, This is the electromagnetic shower profile. This is when we shift the electromagnetic profile, everything to the same, when we plot x minus x max, we see that the the predictions and the observations are coincide very well, except in this region very close to the startup of the shower. And this is where the decoupling of the electromagnetic and the hadronic cascade starts. And this can be used, in fact, to extract some information about the injection of pi zeros. But unfortunately, well, this is a paper published by the Pierre Auger Observatory, and this is this parameter R, which measures basically this velocity of this of the geyser Hillas startup. The difference between proton and iron, this is the two primaries. We see that there is no enough precision yet to distinguish between them. But in principle, this could be possible if we have the better instrumentation in the future. For the rest of the shower, the shape is very, very universal. The shape of the muon distributions at production is also very universal. Here we have the muon production depth. So this is the depth of production minus reference to the maximum. So all the showers are displaced to make the maximum coincide. It's very universal. There are some differences in the tail, but the bulk of production is very universal. Then we have the PT. The PT, look at this, is the logarithmic scale, so it's very exaggerated. Perhaps the bulk of the muons have a very universal PT distribution. And then we have the production spectrum of muons, which is between the three, among the three, this is the less universal of the three distributions when we compare the different hadronic models. And this will have some importance in the things that I will explain later on. So let's jump now to measurements. So one of the first measurements, which this was a work done by the Pierre Auger collaboration, we can compare, we can make we can measure the maximum of the muon production depth. Is a technique which uses the timing, the arrival time of the muons, because they travel in a straight line, so you can make a geometrical reconstruction of the production point, and you can plot at the same time the depth of the electromagnetic shower. So we have here the Auger point, and we have here the predictions of all the compositions in between iron and proton for two hadronic models. So all the possible compositions are here at this energy at 10 to the 19.4. And we see that there is a difference with respect to predictions. And we believe that the problem comes from the X mu max, because as I said, we trust more for composition the prediction of X max. So probably X mu max, the production depth of muons, is wrong, is wrongly predicted by models. So there were some investigations of what happened, what was wrong in the predictions in the physics by models. And there might be some problems with the baryon production, with the pion air diffraction, and also with the kaon and pion energy spectrum, which changed the velocity, somehow they changed the velocity in how the hadronic cascade builds up, how it grows. So this is some implications for something has to be changed, but the feedback, I mean, it's not clear which one of these are the dominant, and there is still some work to do. On the other hand, there is also a big feedback in between the X mu max and X max, a big change, a large change. When you change these parameters, a large change happens in the X mu max and a small change happens in X max. So there is some feedback between these two variables, which can be taken where we can take advantage of to improve the predictions for mass compositions and also for understanding the hadronic physics. And now, one of the most important results, which are the results of the working group on hadronic interactions and shower physics, which is a meta-analysis of the muon surface densities of 9 experiments, which were very different experiments in different conditions of zenith angle, distance to the core, and also energy threshold. So we have to put them, the group had to put them together and make a comparison to check if there was a problem reported, to confirm whether or not there was a problem given that was measured by other experiments on the number of muons compared to predictions. So this new scale was created, which is Z, which is the relative number of the number of muons compared to the predictions of proton, and then divided by the relative difference between iron and proton. So this is a number that goes between 0 and 1. 0 if it coincides with the proton predictions, the same number of muons as in proton, and 1 if you measure the same number of muons as an iron shower. So the experiments, as I said, were very different. So we have some experiments like Auger, which have shower energies measured in optical telescopes, and the muon density is measured in surface detector. We have Auger, Amiga, which is a part of Auger, TA, and Yakutsk. Then we have the shower energy, some experiments which measure the shower energy in the surface detector, and then they measure the muon content with a surface detector like IceCube and Agasa. Then we have experiments which measure the electron density, and then they measure the muon content with the surface detector. The muon content is always measured with the surface detector. There is no other way. What changes is basically how you measure the electromagnetic component, how you get the energy scale of your experiment. So we have Cascade Grande and EAS MSU, and then we have experiments which basically only measure the muon content, like Nebor-Decot and Sugar. So this is the result. So there is one plot for each single model, because the comparison, I didn't say, but this comparison has to be done. The number of muons is compared to the predictions of a given model, and in the denominator, it's given by the predictions given by a model. So this comparison has to be made model by model. So we have this picture for the old models and the new models after the LHC. So there is a bit scattered, it's a bit chaotic, but when we make the energy rescaling of the different experiments, and we do that by comparing the energy spectrum and allowing a freedom of the energy scale, so we match the energy scale, and it doesn't matter much what is the scale, but the important thing is that we make a relative shift of all these scalings, and here are the scalings we have to apply. We use this common energy scale between Auger and TA because of historic reasons, and then we see that the picture improves a bit. The models, the data points align, so the color points are the predictions, are the measurements of the different experiments, and in gray is the number of muons that the given composition, the measured composition, would give in this hadronic interaction model. So it's seen clearly here. Okay, so an axis would be not comparing the measurements with the proton or iron line, sorry. It would be the comparison of the measurement with respect to what this given composition would give in terms of number of muons. So we can do that for these two hadronic models. This is where we have most of the data, and we subtracted the Z, measured Z, minus the Z predicted, assuming a given mass, which was measured by the different experiments, and this is what we obtain. So if we make a fit of this line, we see that the slope of this fit using different statistical techniques and different to see if this was an artifact or this was significant enough. The correlation coefficient between the different models and was checked. Some of the experiments were removed from the sample to see if this trend was still observable, so it survived all the checks. And we see that the significance of the slope is above 8 sigma, so it's completely confirmed. And we can see that the discrepancy, or the muon, what is being called the muon puzzle, starts around 10 to the 16 and reaches to the highest energies with a large excess on the number of muons. Within this group, it was also checked, because we have different experiments with different energy thresholds and different working at different zenith angles. So when you compare showers with different zenith angles, you can also assume that there's a different energy threshold for muons, because the atmosphere is added matter that cuts low energy muons. So if it was there was some, it could be observed some dependency with the energy spectrum of muons. So there was found no evidence of discrepancy on the energy of the energy spectrum of the muons. So there was found no problem using this data. But Cascade Grande reported that the attenuation of the number of muons as a function of the zenith angle was different from expectations. So it's muons probably have a larger attenuation length, so a harder energy spectrum. And if you remember in one of my first slides, the energy spectrum is one of the basic production distributions which has more uncertainties in the prediction of the model. So this is something that we also have to keep an eye on, and there will be quite interesting physics in the short future. So the reasons for this muon energy spectrum, these differences, is perhaps because of the difference in the meson production, in the energy spectrum of the meson production. Also, perhaps there are differences in the pion and kaon ratio in the shower, given that kaon and pion, they have different energy spectrum. If you change the ratio, if the real ratio is different, then you will observe a mismatch in data. The transverse momentum distribution, and I'm speaking about the bulk of particles, which is below 2 GeV. So there is no deviations with respect to universal expectations from the model. So this is a very robust quantity. And I insist I speak here about the PT below 2 GeV, because there are studies and measurements above this for high PT, and you can see them in this review, and there you can examine, you can see that there is interesting physics there, and in fact there are some deviations with respect to predictions, but not for the bulk of particles belonging to the energy shower, and for the bulk of particles which are measured in cosmic ray arrays. And then it was so if we not only measure the average number of muons, if we want to examine the fluctuations, the shower-to-shower fluctuations of the number of muons, we can see that this correlates very well with the first interaction, because the number of muons is basically the multiplication of the basically the number of muons is the multiplication of the multiplicities of all interactions. Also is the multiplication of the different energy fractions, and then normalized by the total energy to the critical energy. But we found, so it was found in this publication, that the thing that best correlates with the total number of muons in shower-to-shower fluctuations is a quantity which is right in between this alpha, which is the sum of the energy fraction to the power of beta, and beta is the exponent that describes the growth of the number of muons with showers. And this is beta is 0.93. So practically this alpha is in most cases, it can be taken as the energy fraction of the kept into the hadronic cascade. And this is where we find the most correlations. And if we allow these quantities, if the total number of muons is the multiplication of these quantities, and these quantities fluctuate shower by shower, we can observe that the total fluctuations of the number of muons is the sum of the fluctuations of all these factors. But then we can see that the fluctuations of this contribution to F2 to Fn are suppressed by the number of participants, because the shower is growing, so the fluctuations get narrower and narrower. Because you have more participants, it grows as the multiplication of the multiplicities grows, as the shower grows. So basically, we can see that 70% of the fluctuations come from the fluctuations of the first interaction, of the energy fraction of the first interaction. And then we can see that, for instance, if showers which no pi decay, where we kept with no pi zero decay, where we get all the energy is kept into hadronic component of the shower, then we don't have basically fluctuations. And this can be used to put limits in Lorentz invariance violation, because if the pi zero decay would be suppressed. So here I report, and I'm about to finish. Here I'm reporting on the measurements of the fluctuations of the number of muons done by Pierre Auger. And here, so these are the measurements, and these are the predictions of the for different hadronic models given the composition which is measured, and we see no discrepancy. So it means that the description of the fluctuations of energy fraction in the first interaction is well described, and this indicates that there is no large, probably there is no large deviations in the first interaction. So the problem with the number of muons is probably accumulation, a small accumulation of a mismatch over the different generations. And this is what it has been studied in this series of articles. So if we introduce a small deviation on the energy fraction in different interactions, for instance, a 5% deviation, and we count 6 generations, which is the typical number for a 10 to the 19 shower, this accumulates to a 30% deviation in the number of muons. So small deviations can produce a large deviation on the number of muons. And this plot here shows the prediction of X max with respect, and here is the number of muons. Here we see the Auger point, and these are the predictions for proton and iron. And then in these articles, they moved the energy fraction up and down, the energy fraction in the first, second, and third interaction, but with a decrease in the importance of this with a smooth, it was not a constant change along all the interactions. It was a change most important for the first interaction, less important for the second, and so on. And they see that it's possible to get to the data point of self by Auger. So the muon puzzle, so this is an indication that the muon puzzle can be solved by increasing the fraction of energy going to the hadronic cascade. And then there is many models in the market, for instance, the stream percolation, the strange fireball, the chiral symmetry restoration. Then there is the core corona, and the core corona, which is quark with gluon plasma formation in this reference. And here you can see that it's possible to reproduce the results of WISP with with values of this effect, which are quite okay. And for instance, this other work here is for the violation of Lorentz invariance. And then you can increase, if you forbid in the Lorentz invariance violation, if you forbid the decay of pi zeros, this would be one of the effects of this invariance violation, then the number of muons would increase, but then you would decrease a lot the fluctuation of the number of muons, because you would saturate the hadronic shower, so you don't have room for fluctuations. The fluctuations come from the fluctuations on energy going to electromagnetic or hadronic shower, and then you would enter in conflict with the measurement of the muon fluctuations, and this can be used to put limits on the Lorentz invariance violation. Then one of my last comments is that we need to go to the to study the full distribution of the number of muons, and this is also a result by the Pierre Observatory. So these are the raw measurements of different energy beams, and in blue are the physical fluctuations after subtracting the detector uncertainties. And in principle, we would be able to observe a distribution that is like this. We are not yet at this moment, but in the future, we will be able to get something like this. For the moment, we are using the average value of the number of muons and also the fluctuations, but we will be able to study the tails of the distributions and the full distribution in detail, which has lots of information on the hadronic interactions at very high energies. And this is an example of that. So these are the distribution of number of muons for proton showers. And we can observe that if we change the energy spectrum of pi0 production in the first interaction, we change the tail of this distribution. So these are shower-to-shower fluctuations. So if we change the spectrum of pi0 production, this will affect the muon content of the whole shower. So we can extract also measurements from the first interaction. And
5 minutes left.
Yes, this is my last transparency, and then its conclusions. And then there is a tantalizing possibility, which has been reported in the last SVECRI conference and also in the last ECRS. And these are preliminary results by Auger. It looks like the best fit to describe the distribution of X max and signal in the surface detector. If you allow some freedom to move the X max, a rigid shift in X max from the models, you would obtain a much better fit. So it looks like the models data is in tension with the models and wants the models to shift a positive shift in X max, which is quite unexpected, and this would change the composition, and of course it would have profound implications for the understanding of the hadronic models, but the results are yet preliminary. And here we see the prediction of the hadronic models, and this would see in dark solid lines is the results of this study, what the models should look like to have a better fit. Sorry, and then the conclusions is that there are important differences in model extrapolations for proton air and pion air, and the proton oxygen would be important in the next LHC measurements. X max is the less model dependent of all the observables, is used to measure the proton air cross sections, and is the reference observable for mass composition. So X min max is sensitive to the cascading velocity, to the hadronic cascading velocity, and among the explanations for the mismatch compared to models there is the pion air diffraction. This is one of the main reasons, and also the baryon productions. There are strong indications of harder muon spectrum in data compared to models, and the muon puzzle. This is the most important result so far, is the mismatch is confirmed with more than 8 sigma by the WISP group, which is collecting results of 9 experiments. And the muon puzzle starts at very low energy, at 10 to the 16. But it looks like this effect is cumulative, and it can be explained by an increase of the hadronic energy fraction over different stages of the shower starting at 10 to the 16. So So this is confirmed. I mean, what I said is also supported by the findings of the fluctuations of the number of muons, which coincide with predictions. And then the last point is that we have to go to study the whole muon distributions, and there will be much more information about hadronic physics when we can reconstruct the full distributions with all details. And I will stop here.